All right. Yes. Yes. Oh. It's all right. It's just, I mean, it's just this number right here, right? This, change that and that. Let me just back up and go to here. 4 over 1, 3 halves times 1/4, flip it, 3/8. 3/8. Okay. Yes?
Why did the square disappear?
Because you're squaring it.
Oh, I see.
Right?
Yes.
So this is just the quotient rule, right? Setup. Any questions on the setup? Derivative of x is 1, so I didn't even put it here. So we just get this. All right, derivative of that, that's a chain rule, and I did that over here. We have composition. So you do outer function is the root. Derivative of the root of something is 1 over 2 times root of that something. Times derivative of the inside is 2x. The 2's cancel. I slide the x on top. That goes here. Then still times x. And then all over this bottom, which is a square root, but then square it, right? So the square root goes away. At this point, we don't really need to clean anything up because we actually know the value of x, don't we, that we want to plug in? So let's just plug 1 into this and try not to screw it up like I did. Plug in 1 into this, right? And when you clean all that up, you should get 3/8. And then this is just that y minus f of a equals slope of tangent line times x minus a, yeah? That's it, that's the equation of line. So we don't want to lose sight of the fact that the whole point of this is to be able to come up with, you know, the slope tangent line and then possibly the equation. All right, let's take a break here. We'll go for, 5-6 minutes, and we'll come back and get into some other stuff. May I erase this? Yes? Okay. How many of you got it? Anyone get that? Okay, quite a few. Did y'all get the derivative?
I was close.
Close? Okay. Yeah. Okay, so let me put this back here. All right, we have a quotient, right? We have a quotient. So the quotient rule says that you will take the derivative of the top one, multiply it times the bottom, then subtract from that the derivative of whatever the bottom is times the top, and then you'll do that all over the bottom, whatever the bottom is squared. So that's just the formula, right? Now I need 2 derivatives. I need this one and this one. If I can get those 2 derivatives, I'm pretty much done with the derivative, right? So derivative of x is 1. And so 1 times this is that. Okay, that derivative is a little more complicated because it's a composition. It's x squared plus 3 inside of the root. So you've got the chain rule there, right? So I do that over here. So the first thing I do is like my hand, right? Derivative of the square root of my hand is 1 over 2 square roots of my hand. Then I'm done with the root. Take derivative of what's inside. Derivative of this is just 2x. Is that all right? These 2's cancel. And then I just slide that x on top. Is that all right? Because this is really like x over 1, so you can just multiply across. That good? So that piece is right there. And then we still have times x. Don't forget that part, right? And then when I square, because this is a square root, I'm squaring it, the root and the square go away, we get this.
Okay.
Yeah? And that's our derivative.
Okay.
You sure?
Yeah, and then you just plug in.
Now I just plug 1 in, and like I said, try not to screw that up. And then you get 3/8. And then once you have that number, then that's the slope of your tangent line, then you use your point slope equation of the line.
I tried to do this over here. Like, I don't know why. Like, I started with this, and I did this,
Okay, you can do that.
and then I got this, and this.
Okay, so here's the problem with, well, not the problem, but let me show you your way, okay, because you can actually do it that way. Your answer is going to look different than ours here, but it will still be the same answer, all right? So what you chose to do is not look at it as a quotient. You decided to leave the x there and bring this up as an x squared plus 3 to the negative half. Is that what you had written? Yes? If you're going to do it this way, you have to realize right here is a product.
Right,
And so you have to do the product rule,
and not change.
and not the chain. Well, the chain will come too. But at what point, right? Here's our product. So according to the product rule, you have to do derivative of the first one times the second one plus now the derivative of this one. So, right? Then times the first one. So that's what you have to do, right?
Yeah.
Now when you take derivative of this, you just get 1. So this is just x squared plus 3 to the negative 1/2. And then over here, plus, all right, we'll do some scratch work on the side here, right? We've got to take the derivative of this, right? So you have something to a power. The power comes out. Right? Power comes out. Subtract 1 from that. Negative 3 over 2. Times the derivative of what's in here, which is still 2x. Do you follow that chain rule?
Yeah.
All right, these 2's and the half go away. So you wind up with, let's see, negative x times, yep. I'm just going to do this to the negative. I'm going to leave it, just leave it like this, okay? Okay, so that's going to go here. Can I change that to a minus now? Minus, and then it's x, and then x squared plus 3 to the negative 3/2, right? Times another x, right? So I'm going to just move that out front and make that x squared. That's your answer.
Oh, okay.
That's your answer. Now, why is that the same? What happens if I plug 1 in here? 1 squared is 1, plus 3 is 4, right? So you have 4 to the negative 1/2 minus, now plug 1 in here, 1 squared is 1. 1 in here is 4, so you have 4 to the negative 3/2, right? And that looks crazy until you realize that that's just 1 over 4 to the half minus 1 over 4 to the 3/2, just dropping the negative exponents down. Right, that's what 4 to the negative 1/2 is the same as 1 over 4 to the positive 1/2. Same thing here.
Yeah.
And then now this is just 1 over, raising something to the half is the same as the square root of it. And then minus over here, this is the same as the square root of 4, but then cube that answer. That's what this means. So square root of 4 is 2, so this is 1/2. Minus, this is 2, but then cubed, so you get 2 cubed is 8, so 1/2 minus 1/8. And if you get a common denominator, you wind up with 3/8. So you see you get the same exact answer? Yeah. Okay. I personally do not like bringing things from the bottom up, only because when you do it, a lot of times your answer is going to have negative exponents, and those are just a little harder to work with for most students than the positive. But, I mean, mathematically, it's the same thing. We have about an hour. Please do not let me go past 3:50. Let's stop about 3:50, all right? All right, we are going to say that we are officially done with chain rule, although you need to go practice and do your homework, all right? That's one of the unfortunate things about this summer 8-week format. Like I told you, you don't have time to go practice this, and now we're going to move on. So before I transition into the next section, 2.6, I want to show you something that some of you may or may not have seen. It is related to the course. This is not just random useless information, but I want to see if anyone has ever seen this before. Does anyone know what that means? 4 mod 3. Anyone ever seen that? 4 mod 3?
Like Mod's Pizza?
Mod pizza. Mod pizza, exactly. Anyone know what that means? 4 mod 3? No? Okay, good. So we get to learn. Computer science majors? No? Yeah, it has something to do with it's called modular arithmetic. So here's what this means. This means if you take the number 4 and divide it by 3, what would you get? So 4 goes into 3 one time, right? And then you go 1 times 3 is 3. We're going back to like basic elementary school, right? Subtract the 3 and you're left with 1, right? And then if you wanted to keep going, you could do decimals. But back in elementary school, you would say, okay, that's your remainder, right? So you put R1. Remainder 1, right? 1, remainder 1. So 4 mod 3 is equal to whatever remainder you get here. So if our remainder here is 1, so the answer is 1. All right? What's 5 mod 3? Should be 2, right? Because you're just going to do 5, divide that by 3. That goes in once. Here's 3. You subtract. Oh, you have a remainder of 2, right? So you should get 2 here.
Is mod like MOD?
M-O-D.
Is it for something? Like each of
It stands for this operation of giving you the, when you say 5 mod 3, you're saying what is the remainder when you take 5 and divide it by 3. So it's a mathematical, it's a mathematical expression that has the meaning of giving you the remainder. What's 6 mod 3? Well, what's your remainder?
0.
Nothing, right? So you get 0. Okay? Understand? 7 mod 3 is 1, right? 8 mod 3. 2. Let's go another one. 9 mod 3. 0 again, right? Understand what's happening here? It's always giving you the remainder, right? So what?
There's a pattern.
Yeah, there's a pattern, right? What do all the answers that give you 0, what do they all have in common? 6, 9, those are all multiples of 3, aren't they? Those are all multiples of 3, or you could say they're divisible by 3, yes? And what about the ones that have an answer of 1? They're these numbers, but just plus 1, right? So it's like 6 plus 1 is 7. What would the next one be? We would have to have what, 10 mod 3? 10 mod 3 would be what? 1. See, so the ones that have 1, these are just one more than the ones before. All right, so where is modular arithmetic useful? All right, you ready to see? If y equals sine x, find that. What am I asking you for? Does that mean raise it to the 3,215th power?
Yes.
No. Remember, the parentheses means something different. If I put a parentheses around that number, it means what? That's the derivative. I want the 3,215th derivative of sine. So I want you to take the first derivative, then the second derivative, then third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, right? I want you to do it all the way till you get to 3,215. And no one feels like doing that, right? But let's at least start the problem. all right? So what is y0? That's the zeroth derivative, right? That means don't take the derivative. That's the original function. What's the first derivative? Cosine x. Okay, careful. What is the second derivative? Negative sine x. Okay, very careful. What's the third derivative? Negative cosine x, right? Because this negative 1 comes for the ride, right? Derivative of sine is cosine. So now we have a negative cosine. Yes? The fourth one, we go back and we get back to sine, don't we? And now, isn't it just going to repeat itself, this pattern? Right? So the fifth derivative, right? The fifth derivative would be cosine x. The sixth, okay, so wait a minute. This is, let me do this way. If I do, here's my derivative, and here's the answer, then if I do the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? The zeroth derivative give me what? Can I just put s for sine? Next one was cosine, then negative sine, then negative cosine, then sine, cosine, negative cosine, sine, cosine, negative sine, negative cosine, right? Y'all following me? So every fourth one, right? So what I'm going to do here is I'm going to look, let's see where I get sine from. I get sine when I have the zeroth derivative, right? I have sine when I have the fourth derivative. I have sine when I have the eighth derivative. And I have sine again where? Where would it be? 12th derivative, right? All of those numbers are divisible by, or you could say they are multiples of 4, right? So when I do that number mod 4, I should get?
Sine.
No. When I do 0 or 4 or 8 or 12, any of those numbers mod 4, the answer is 0, right? Y'all following me? No? Okay. So let me see if I can't generalize this. So if we're taking the nth derivative, right? The nth derivative of this, here's what's going to happen. I'm going to have a couple of different scenarios, right? I'm not telling you what derivative I'm taking. I'm just saying I'm taking the nth derivative. I know that the answer is going to be sine of x if what? When I take that derivative and mod it with 4, I get 0. Right? I'll always get sine if I take this number and mod it with 4 and get 0. Now, the answer will be cosine if what happens? Cosine, right? Cosine. If when I mod that number with 4, I get 1, right? So if I mod that derivative with 4, I get 1. And then for negative sine, if I take the derivative and mod it with 4, I get what? 2. And then last, it'll be negative cosine if I take that n, mod it with 4, and get 3. Why did I mod 4? Why do you think 4 is important? The cycle was 4, wasn't it? It took 4 to complete the cycle. 4, it was sine, cosine, negative cosine, 4 things, and then it repeats. 4 things, 4 things. If it had been 3 things, 3 things, 3 things, then we would mod 3. If it was 8 things, 8 things, 8 things, we would mod 8. That kind of make sense? So now, can we answer the question? Yes, what are we going to do? Take that number and divide it by 4 and see what our remainder is. What is it? 1? I'm going to do it by hand just for fun. Okay, so here I divide this by 4. Let's see. Goes in there 8. Right? What is it? So What, I thought I heard someone say something. What, 800?
It's negative cosine.
803, right? 803. And your remainder will be 3. And so now you know that your answer is negative cosine without ever having to take 3015 derivatives. That's pretty neat, right? That mod thing. I mean, it's... All right. Because when we did this derivative that we were asked for, and we modded it with 4, we got a remainder of 3, we knew that it fell into this category, and that category is what gives you negative cosine. And now you could do any derivative, couldn't you? Right? All right, that was like a little off-topic, on-topic thing. There is a problem like that in one of the homework assignments where they ask you for like the 95th derivative of cosine or something, and they don't talk anything about modular arithmetic at all. They just expect you to find the pattern and somehow figure it out. So the mod would help you with that problem if you get to it. So for who's computer science? Just one? That's crazy. Normally it's like half the class. So like I have a watch, a smartwatch, and there's a program where I can create do a custom face on my watch, and I have it set so that if my battery gets below a certain percentage, it'll start flashing to let me know, and I have it flash every 3 seconds. And so what I do is I have the watch, the brains in here say, look at what second it is, right? Like right now, if I look, there's a certain second, like it's 43, 44, 45, 46, right? I have it take the second and mod it with 3. And if that answer is 0, then it doesn't flash. If the answer is 1, it doesn't flash. If the answer is 2, then it flashes. So that makes it flash every 3 seconds. That's the way a computer scientist would use modular arithmetic. All right. I'm about to start the next section, but I'm going to give you this. It's not a trick question. What's the derivative of this? Cosine x, right? Now, I want you to realize that we actually did just do the chain rule, because we have an inner function, right? And we have an outer function. The inner function here is what? X, right? So what we did is we started with the outer function. What's derivative of sine of something? Cosine of that something, right? Then times, now you're going to take the derivative of this, right? And what's the derivative of x? 1, right? It's 1. So you actually did have, we were doing this chain rule without even knowing we were doing the chain rule. And this works for anything, right? Like even if I do this, ask you for the derivative of that, you're just going to tell me what? 8x to the 7th. But technically, what's happening here is that you have something to the 8th power, right? My hand. And then you bring the 8 out, and then my hand to the 7th, then times now the derivative of the x. What's derivative of x? 1. And so there was a 1 sitting out there, wasn't there? The only reason why this is a 1, right? The only reason that we're getting 1 here is because I'm asking you what the derivative of x is, and everybody is saying 1, right? Everyone is saying 1. And if we go to Leibniz notation, we can understand why it's 1. What is the derivative with respect to x of x? Well, 1, right? And the reason why is because this x kind of slides up here and we get dx over dx, and that's why we're getting 1, right? It kind of makes sense. We're taking the derivative of x with respect to x. So it's like I'm saying, how much does x change by if x changes by this much? Well, then it changes by the same amount. It just changed. So the ratio should always be 1. Eh? So I'm now going to restate these problems. These two problems, I'm going to do them again, but I'm going to use a different notation. So I'm going to use dy dx, right? So I want to find the derivative of this with respect to x. So using the chain rule, it's the outer, derivative of the outer times the inner function times now the derivative with respect to x of the inside, which we just said is 1, right? I know this seems like maybe I'm overkill and I'm trying to confuse you. I'm not trying to confuse you. It's where we're about to go that I want to make sure you understand that this chain rule has been happening the whole time. All right. With that, I think I'm ready to bring up my notes for the next section. 2.6. Notice I did not put notes up for 2.5. Because the chain rule is just one note, right? There's the formula. That's it. There's nothing more in chain rule. But 2.6, there's actually some. I do have notes for chain rule here, but like I said, it's not a whole lot. Come on, hurry up. All right, 2.6, implicit differentiation. So everything that we've been doing so far, everything that we have been studying since we started this class is our functions, right? We have been dealing with functions. Y is some function of x, right? So we would say that we have an explicit function or an explicit equation. But not every equation is explicit. So the best way to look at this is to look at some examples. Look at the first example here. This first example, we would say that y is a function of x. Because if somebody gives you x here, right, y is a function of x. Because if somebody gives you an x, right, if somebody gives you an x, so if this is given, then you can figure out what y is, right? Right? Somebody hand me x, 5. Okay, 3 times 5, 15, plus 1, 16. So if you give me x, then I can provide you y, right? So y is a function of x. This is supposed to be a square root. All right, what about the next one? Is y a function of x here? If somebody hands me an x, can I then determine what the y is? Yes, right? I just plug x in, boom, and I can figure out what y is. So again, this one is also y is a function of x. Somebody gives me x, I can figure out what y is. Now what about this one? If somebody gives me x, can I figure out what y is? Not easily, right? Maybe, right? Maybe, but not easily. But what about if someone gives me y? Someone gives me y, it's going to be easy to tell what x is, right? So here I would say that x is some function of y. I'm not going to call it f, I'm going to call it g of y. So that means that if y is given, then you can find x, no problem, right? Mostly everything that we've looked at has been a function, right? Everything we've studied all the way up in this class through pre-cal, we've been dealing with functions. But there are other types of equations that are not what we call explicit. Explicit really means that you can solve for one of the variables. You'll notice on all three of those, this one is solved for y, this one is solved for y, that one's solved for x, right? But look at these equations. Could you solve this for y? Could you?
Yes.
How? How would you solve that for y?
Move x squared over.
16 and
Okay, move the x squared over to the other side. So subtract x squared on both sides.
Take the square root.
Take the square root. But you're about to run into a problem. Because when you take the square root, what happens?
You get 1 minus x.
Can't do it that way. You can't, because there's subtraction, you can't do the square root of each one. What happens when you bring a square root on both sides of an equation? What do you have to do? When you initiate a square root, plus or minus, right? You're going to have to do a plus or minus. So if you initiate a square root on the left and a square root on the right, you must do plus or minus, which means this is plus or minus this, right? And this is no longer a function. Why? If I plug in a number here, how many things come out? 2, right? I get a positive and a negative. And remember, functions is one input, one output. One thing goes in, one thing comes out. And so this is no longer a function of x, right? So if this is y is not a function of x, because if x is given, then what? There's 2 y's, right? There's 2 y's, and that violates what a function does. I always look at functions like car washes, right? A car wash, right? There's certain things you can put into a car wash, right? Like cars. Certain things you can't. Like 18-wheelers can't go into like your neighborhood car wash, right? So that's a domain restriction, right? And then when you put a car in, you get 1 car out, right? You don't get 2, right? If you get 2, then you're going to make a lot of money. But you know what I mean? So that is not a function of x. And if you try and go the other way and solve for x, you'd run into the same problem because you'd wind up square root again. So that right there is not an explicit equation because you cannot easily get x or y by itself. How about this one? Very difficult to get x by itself or y by itself. Very hard to do. And this one is actually impossible. It is impossible to solve this for x or y. Can't do it. I mean, you can try. There's no algebra you've ever learned in that I could ever teach you to solve for x or y in these. So there are many types of equations out there that are not explicit, and therefore, when you graph them, they look different than our normal functions. So I'm going to go to Desmos, and I'm going to have Desmos graph the first implicit one there. X squared plus y squared is 16. I know all of you know what that is, right?
Circle.
It's a circle of radius x squared plus y squared. What happened? Plus y squared equals 16. Desmos, you can just type in the equation. There we go. X squared plus y squared is 16. It fails the vertical line test, right? This fails the vertical line test. But, I mean,